Section 3.8 deals with an application of derivatives known as Newton's method. With Newton's method, we're basically trying to find zeros of a function. So recall that zeros of a function are values such that when we substitute them into our function, it gives us 0. For example, if we have the function f of x equals x squared minus 4, if we substitute a 2 into that function, we get 0. If we substitute a negative 2 into that function, we get 0. But it's not always quite as simple to find values that make our function equal to 0. If we have functions that are not factorable, this one, even though it's factorable, if it was quadratic but not factorable, we could still use a quadratic formula to get zeros of it. But if we have something that were cubic or a combination of trig and other expressions, then it would be more complicated to find zeros of those functions. So let's look at how Newton's method is going to work. Let's suppose we have some function. Just sketch a graph of a function. Let's try that graph again. Maybe something like this. And we want to find what makes that function equal to 0. So let's start out by calling that function f of x. So if I don't have an idea, I'm just going to pick an x. Keep in mind that when I do this, I'm probably not going to have a graph. I'm just going to have the equations. Let's imagine drawing a tangent line. Now, if we have a function that's some messy function, then I might not know how to solve that once I set it equal to 0. But if I have a linear equation, I'm just going to make some numbers up here. This is something that if I were to let y equal 0, I could solve that equation very easily, where something like y equals x cubed minus 3x squared minus 4.2x plus 1, that might be a lot harder to set equal to 0 and solve. So we're going to make use of tangent lines to approximate x-intercepts, also known as zeros of a function. Keep in mind, at that x-intercept, we have an x value there, but the y value is 0. So once we find that value, we're going to let that be our next guess for our 0 of the function. And then we're going to draw a tangent line to our graph there. And notice this new point, that x-intercept is closer to the actual 0 of the function than that one is. So each time we go through an iteration of this, for lots of functions, particularly if we make a relatively decent initial guess, we're going to be getting approximations that get closer and closer to the actual place where our function touches the x-axis, which is known as the 0 of that function. Now we can demonstrate that in MathCAD. Let's suppose that we have this graph, I'll zoom out a little bit. That's a graph of this equation, y equals 1/2 x cubed minus 0.6. So we have right there a 0 or an x-intercept. So we can come in, if we don't know where to start, and make an initial guess. Here I've made an initial guess of 2. So this is plotted a point on our function. Not sure what happened there. Plotted a point on our function where x equals 2, and then it drew a tangent line. So this is our new approximation. Notice that's what it says, our 0 approximation. So this is about 1.433, so forth. So we're going to use that as our next guess. So this x value here is 1.4333. It draws a tangent line, and this is our next approximation, 1.150, etc. Notice that's getting closer to the actual value, the actual place we touch the x-axis. I'll do another one. This will let me scoop this over and zoom in. Notice that's even closer. So this is what the new approximation is. What I've calculated here is if we take that approximation and plug it into our function, this lets us see, well, how close to 0 is that value. So it's pretty close. This shows us the distance between our previous guess and this one. Each time we go through that, that distance should be getting smaller. So our new approximation, and I don't even know if I can zoom in close enough to really see that. Let's recenter our graph. I mean, that's so close to the actual x-intercept. Notice if we plug that value in, we get 1, 2, 3, 4 zeros before we get our first non-zero number. So that's really, really, really small. And that shows us how close we were to the previous guess. So each cycle through this, these are called iterations, gets us closer and closer to the true 0 of the function. Now this is called a numerical approach to finding an x-intercept. So we might not ever get the exact value. For example, if our value is a rational or an irrational value, for example, the square root of 3 over 5 or pi over 7, that's an irrational number, and we're not going to get that exact value, but we can get a decimal approximation to however accurate we need it to be. If we need it to be to the nearest tenth or the nearest hundredth or the nearest thousandth, basically we keep going until 2 successive iterations give us the same answer to that many significant figures. So like to the nearest hundredth, we're at 1.06. If we do another iteration, we're still at 1.06. Another one, 1.06. So if we only needed to be accurate to the nearest hundredth, then there we are. We've gone through enough iterations that each step is making such a small difference that we can be sure within a certain amount of error that is our answer. So let's see how this is going to work algebraically. So let's sketch the function again. I'm going to pick a point on there, and I'm going to call that x sub 0. And if our function is f, then the y value there is f of x sub 0. So we want to draw a line tangent to the curve at that point. So keep in mind that to calculate the equation of that line, we're going to use the point slope formula. We have a point, that's our initial guess, and the y value at our initial guess. And of course, we get that y value by plugging that number into our original function. And then you may remember that the way we get the slope of that line is to take the first derivative. So the slope will come from our first derivative. We want the slope specifically at that x value, so that's what gets plugged into our first derivative. So if we substitute that information into the point slope formula, then our y value is f of x sub 0. Our slope is f prime at x sub 0 times x minus, then our initial guess we call x sub 0. So that's the equation of that tangent line. So remember, what we're using that tangent line for is to get an approximation of the 0 of that function. Now this one, you can see the 0 of the straight line and the 0 of the function are not very close at this point. But since straight lines are easier to work with, we're just using that line to approximate our function close to the x-axis. So let's find out what the x-coordinate is here, and that'll give us our next guess. And then we'll go through this again. So on the x-axis, keep in mind that our y value is 0. So if we take our equation of that line and substitute a 0 in for y, let's call this x value x sub 1. So this was our initial guess of what makes our function equal to 0. And this is going to be our next guess. So when y is 0, x, we're going to call that x sub 1. So 0 minus f of x sub 0 on the left is basically minus f of x sub 0. So let's divide both sides by this, because we're trying to get x sub 1 by itself to find that next guess. So on the right side, those cancel, leaving us x sub 1 minus x sub 0. On the left side, we have minus f of x sub 0 over f prime of x sub 0. So then to get x sub 1 by itself, add this to both sides. So x sub 1 is x sub 0 minus f of x sub 0 over f prime of x sub 0. So if you tell me what your original guess is for the x-intercept, or the 0, I can plug it into this formula, and that'll tell me what my next guess is. And then we'll take that value, we'll repeat the same process. We'll draw a tangent line there. This x value is the one that we found in the previous step, x sub 1. The y value is f of x sub 1. The slope of that tangent line is f prime at that x value, so x sub 1. And we're going to use that to lead us towards our next approximation of the 0, or the x-intercept. So basically, if I put x sub 0 in to this, it gives me the next value. If I were to put x sub 1 into this formula, it would give me x sub 2. If we take that and substitute it in, it would give us the next approximation. So we go through that iterative cycle as many times as necessary until we get within the desired level of accuracy. So the first part of using Newton's method is to understand what's going on. We're approximating the 0 of a function by finding the 0 of a tangent line, which is an approximation of that function. Not a very good approximation, but we're trying to find a tangent line that has a very similar x-intercept. So as we keep going, I guess our next one would be here. And notice that x-intercept is very close to the actual x-intercept of the function. So as we go through a few cycles of this iteration, we're getting tangent lines that are better and better approximations of the 0 of this function. Now let's look to see an application of Newton's method. So let's suppose we have the function x squared minus 3, and we're wanting to find one of the roots of this. So let's think about what it is we're looking for. If we set this equal to 0, 0 equals x squared minus 3. If we were to add 3 to both sides, we get x squared. So we're basically looking for the square roots of 3, which, of course, are not integers. So by finding zeros of this function, we're effectively finding the numeric values of the square root of 3. Of course, the square root of 3 is the exact 0 of this function, but we want to find out, well, what is the square root of 3 as a decimal? So if we look at Newton's method, if we have a guess, then the next guess, sorry, I got my numbers backwards. The next guess comes from taking our original guess minus our function evaluated at our initial guess divided by the first derivative at that guess. So we look back where we had done it before. So the next one, so if this is x sub 0, the next one comes from taking x sub 0 minus f of x sub 0 over f prime of x sub 0. And we said that's true for any value. If we want to look at the second guess, we take the first one. If we want to look at the third guess, we put the second one in, and so forth. So they give us a value to start with. They say, oh, I'm sorry. I forgot I made up this problem on my own. I just got through eating lunch, so I'm a little off my game. But let's suppose we start with the initial guess of 2. So let's let our initial guess be 2. So the easiest way to keep up with this is to make a table. So let's put our initial guesses here, and then let's put the value of our function when we plug that in. Then we can put the value of our derivative when we plug that value in. And then we can put in that ratio. And then lastly, our guess minus that ratio. So that'll give us the next value. So our first guess, we're going to start with a 2. So let's organize this stuff just a little bit. So our initial guess is a 2. So we need to substitute a 2 into our function. So 2 squared is 4. 4 minus 3 is 1. We also need our first derivative. Our first derivative, bring that to 2, x to the 1 less power. So our first derivative is 2x. So if we substitute our value in for our first derivative, f prime evaluated at 2 would be 4. So to calculate our ratio, we take the value of our function divided by the value of the first derivative. 1 divided by 4 is 1/4, or 0.25. So now lastly, to get our first iteration approximation, we take our initial guess, 2, minus that ratio. So 2 minus 0.25, 1.75. So that's what we're going to use for our next guess. So we're going to keep going through this until we get the degree of accuracy that we require, and let's get accurate within 100. So we're going to take 1.75, plug it into the function. So 1.75 squared, 3.0625. Take 1.75, plug it into the derivative. So 2 times 1.75, I believe that's 3.5. So if we take the ratio of these, this one divided by that one, 3.0625 divided by 3.5, and we get 0.875. Let me just check, make sure. Yeah. So 3.0625 divided by 3.5, 0.875. So our next guess, 1.75 minus 0.875. That 0.9, 1.75 minus 0.875. Having a hard time with a calculator. 1.75 minus 0.875 is 0.875. Okay. I looked at the decimals wrong. I'm a little rusty today. So use 0.875. That's going to be our next approximation. So put 0.875 into our function. And I see what I did wrong on the last one. So I'm sorry. I'm in the hospital right now doing these and haven't had much sleep. I try not to make any more mistakes for tomorrow. So 1.75 is what we plugged in here. What I didn't do is after I squared that, 1.7 squared, I didn't subtract the 3. So 0.0625 is what we should have there, not 3.0625. Now the good thing about this, I guess maybe it's a good thing I did that wrong, is that if you were to make a mistake, then chances are you're just not going to be very close when you get that value at the end of that iteration. So it's just going to take you more steps. So if you do a wrong calculation, then after that one, then hopefully that's going to start bringing you back in closer to what you need. So 1.75 times 2, that was 3.5. Now when we take that divided by 3.5, that looks a little bit better. 0.0179. 0.0179. So if we take our previous guess minus 0.0179, 1.7321. So notice we're the same to the nearest tenth, but we're different to the nearest hundredth. If we were only required to get to the nearest tenth, we would about have it. Now, technically, this rounds to 1.8 to the nearest tenth, so we would still be off a little. But we need to go until in 2 successive iterations we have the same number in the hundredths position if we're trying to get within 100. So this will be our starting point. So we're going to take that and plug it into our function. So our function says square that number, subtract 3. So 0.00017. We're also going to substitute that into the first derivative. So 1.7321 times 2, 3.4642. Now if we take that ratio, 0.00017 divided by 3.4642, that's really, really small. That's 4.9 times 10 to the negative 5. 1, 2, 3, 4, 5. So take our initial guess on this iteration, minus 0.00049. So that the opposite of that combined with 1.7321, 1.7321 to the nearest 10,000. So that's actually accurate to the nearest, at least to the, we could say to the nearest 1,000th, really to the nearest 10,000. So the 0 of our function, we can say to the nearest hundredth is 1.73. So that's roughly what we said that this actually represents, the square root of 3. So let's just check that. We take the square root of 3, 1.7321, or in our case, 1.73. So yeah. So this is a numeric way to evaluate some irrational numbers, such as square roots and other things, without having to just guess, square them, see how close that is. So technically what we're doing is we're finding zeros of a function, but depending on how we write our function, we can make that represent various things. Now that we've finished this, some of you might have picked up on the fact that there are actually 2 different zeros to this. When we worked this out algebraically, we saw that plus and minus the square root of 3 were zeros of that function. So why didn't we get both of those? Well, our initial guess is going to determine which zero Newton's method gives us. Our parabola, f of x equals x squared minus 3, looks like that. And if we pick an initial guess over here, then as we draw our tangent lines, those are going to be getting closer and closer to this x-intercept. Where if we were to have picked an initial guess, perhaps right there, that would be getting closer and closer to this one, to that x-intercept. So our initial guess is going to determine which particular zero we're narrowing down on. If a function has multiple zeros, then we might have to go through this process several times using different initial guesses. So that can be a little bit tricky. Also, one thing that we have to be careful of, bring this up, is occasionally we can pick something that if we pick that particular number, we end up, the iteration fails. Notice if we were to draw a tangent line to our curve at that vertex, that approximation is not going to have any x-intercepts. If we think about it, the slope there is 0. So when we plug into our iteration, if our slope is 0, always at that particular point or line, then that's going to be undefined. When we plug our first derivative in for that line, we're going to get an undefined answer, which means that the method fails. Also, there are some cases where I probably won't be able to draw one that's exactly what I'm looking for. Sometimes we might pick a point, and when we draw, let's see, that's not what we're looking for. Let's draw something more like this. So if I pick a point here and draw a tangent line, that's going to give us something down here. Depending on how steep this part here is, if this were more sloped, then when we use that, that might be taking us away from a particular zero. So sometimes when we pick guesses, they bounce back and forth, back and forth, back and forth. Now, fortunately, that does not happen a lot. So most of them, even if we bounce a little bit away on the first guess, it's generally still going to narrow down to one of the zeros. So let's look in the book real quickly. Look at doing one more. Let's see. Let's see, which one do we want to do? Let's do this one right here. X cubed minus cosine x. X cubed minus cosine x. What do the instructions say? Approximate the zero or zeros of the function. Use Newton's method and continue the process until two successive approximations differ by less than 0.001. Then find the zeros using a graphing utility and compare the results. So let's just graph that. X cubed minus cosine x, just to kind of get a picture of what our graph looks like. Zoom out. If you think about this function, x cubed minus cosine x, cosine, the smallest cosine ever is -1, the largest it ever is +1. So no matter how large x gets, this is going to be relatively small, where this can get really, really large in the positive direction, really, really large in the negative direction. So that term really dominates the tendencies of our graph. So this is, in general, what our graph looks like. So fortunately, on this one, we only have one 0, it appears. Now on the test, usually I'll say, hey, find this number of zeros of the function, or find the 0 of the function using this initial guess. So let's take our first derivative. Our first derivative, if we bring the 3 down, x to the 1 less power, minus the derivative of cosine is negative sine. So our first derivative, 3x squared plus sine x. So one thing that I'm not going to let my initial guess be is 0. Because if I were to plug a 0 into the first derivative, I would get a 0 here. Sine of 0 is 0, so we would get a slope of 0. Keep in mind that if we have a slope of 0, then this blows up. We are undefined when our slope is 0. So I'm not going to use that as an initial guess. But not knowing off the top of my head without looking at a graph, I don't really want to just start with picking a really large number, so let's let our initial guess be 1. So let's make a table, and I guess we could copy this one. You know what? Let's do this. Let's see if we can erase the values out of the bottom, and then we'll just copy what's left. So, all right, so we want to fill in this table. So our initial guess, we're going to use 1. So if we substitute a 1 into our function, we're going to have 1 cubed minus cosine of 1. Now we have to be careful here, because when we calculate sine or cosine, the numbers that we're substituting in, notice this is not in degrees, so we need our calculator in radians. So when we plug in 1 cubed, of course, is 1, minus cosine of 1, it's about 0.4597. Now when we substitute a 1 into our first derivative, 1 squared is 1, 3 times 1, that's 3, plus sine of 1. So 3 plus sine of 1, 3.8415. And you might ask, well, how many decimal places do we need to keep? We kept a little too many probably on the last problem. If we're needing to be accurate to the nearest thousandth, then that's 3 decimal places, then let's keep 4 decimal places. All right, so it's kind of cut off. I guess I erased a little bit of this. So this is the ratio, this divided by that. So 0.4597 divided by 3.8415, 0.1197. So 1 minus 0.1197, 1 minus 0.1197, 0.8803. So that's going to be our second guess. So we're going to guess that. So we're going to substitute that into our function. So 0.8803 cubed minus cosine of 0.8803. So 0.0452. Then we're going to substitute 0.8803 into our derivative. So 3 times whatever we get when we take 0.8803 squared. And then we're going to add that to whatever we get when we take 0.8803 and take sine of it. So if I type that correctly, 3.0957. So now we need that ratio, 0.0452 divided by 3.0957, 0.0146. 0.8803 minus 0.0146. 0.8657, which is fairly close to what we had on the previous one. Now, one thing you might have picked up on is that this ratio, that's how much we're changing each time. This was our previous guess. We're changing by this amount. So this guess is this far from that one. So our new guess, 0.8657. Substitute that into our function. So 0.8657 cubed minus 0.8657, take cosine of it. So that's 6.7998 times 10 to the negative 4. So 1, 2, 3. 6, 7, 9, 9, 8, 6, 7, 9, 9, 8. Yep. 1, 2, 3, 4. So yeah, that's correct. Now we're going to take our starting value, 0.8657. We're going to square it and then times 3. Plus whatever we get when we take sine of that, 0.8657 sine. So 3.0099. So 0.00067998 divided by 3.0099. Again, this times 10 to the negative 4. 2259. So 1, 2, 3, 4. So that's our ratio. So our initial value, I'm not going to write that out, but 0.8657, our starting value for this iteration, minus our ratio, 0.8655, 0.8655, and to the nearest thousandth, notice both of those round up to 0.866. This rounds that up to 6, this rounds that up to 6. So to the nearest thousandth, x is 0.866. Which we had a graph. We went through several iterations. That's what this is narrowing down on, 0.866. Turns out if we go far enough, that's actually going close to 0.865. But with a number of iterations, 0.866 to the nearest thousandth.